Hello learners, welcome to the next session on quantum machine learning. Now we are going to see about what are the different kind of quantum machine learnings are available and how we are going to work with that, and we are going to discuss about the performance of the QML. So the first one is a pure quantum machine learning. Pure quantum machine learning is very important to design to work entirely on quantum system, and here we are going to maintain quantum states and all kind of quantum operation to be taken place in this machine. So key feature is both data and processing remain quantum. Fully it is related with the superposition, entanglement and interface, and we are going to work with the quantum native data or the efficient classical to data quantum data encoding methods are also to be implemented. So the example is quantum neural network, quantum autoencoders, quantum Boltzmann machine, quantum principal component analysis, quantum support vector machine. Advantages is we can easily exponential speed up in solving specific machine learning tasks. Quantum native problems like quantum chemistry and quantum materials, we can directly have the direct application and we move on it. Next, the challenge is quantum hardware with a high qubit is very important here. That is the biggest challenge, and we can easily go with all kind of classical application, but we are going with quantum data. So that is the biggest challenge here. The next thing is hybrid classical and quantum machine learning. These algorithms combine quantum and classical techniques. So definitely everything to be aligned with quantum principles. Here classical data is pre-processed and or post-processed using classical system. Quantum computing is used for computationally intensive tasks like optimization or feature mapping. It is especially useful for a near-term noisy intermediate scale quantum device. Example is VQZ, variational quantum classifier, quantum kernel methods, quantum enhanced reinforcement learning, hybrid quantum neural network. So advantages is practically with the current quantum hardware and bridge the gap between classical and quantum methods, enable speed up in specific super problems such as optimization or sampling. The best challenge here is interfacing between quantum and classical system, overheads in converting data between classical and quantum formats. The third one is quantum inspired machine learning. These are the classical algorithms that are fully involved with quantum principles but simulating quantum properties on classical hardware. So here does not require any quantum hardware. We can easily go with all kind of quantum properties, entanglement and superposition designed to solve classical problems using different quantum mechanics. So example is tensor network quantum inspired optimization algorithm, quantum inspired SPD, singular value decomposition, quantum inspired Markov model. The best advantages here is applicable for all classical infrastructure, often achieves better performance or scalability in traditional methods, but does not suffer from quantum hardware. So here we are just added all the comparison of three process: pure quantum, hybrid classical quantum, quantum inspired. We can have a different kind of features here when compared with the hardware requirement and compared with the scope, processing methods and data source. So as per the discussion, pure quantum fully need of advanced quantum computers, hybrid classical quantum requirement of NISQ, classical quantum inspired required classical systems. So processing methods in pure quantum we can go for fully quantum. Hybrid classical quantum we are going for mix of classical and quantum. For quantum inspired definitely we are going with simulation of quantum phenomena. This pure quantum definitely used for quantum chemistry and quantum simulation cryptographic application. Hybrid classical quantum especially for reinforcement learning and optimization classification. Next, quantum inspired is especially for large scale data analysis and physics based problem. So working of QML, this is very important. How this quantum machine learning to be worked. First, data encoding maps classical data to quantum state. In the next is quantum processing. The first one is quantum circuit design, quantum algorithm execution. The third is measurement and analysis. So in the measurement of quantum states to be measured and the analysis of measurement results. The next is classical post-processing, conventional to classical output, post-processing evaluation. The next is integration optimization. We have to go for iterative refinement and parameter tuning. And last, we are going to combine with the integration with the classical system, integrating with the ML and deployment and application. This is a general way of working with QML. In the working of QML, in the classical ML model, the classical data is entered into machine learning algorithm and we are directly go on to the prediction. In quantum-based machine learning algorithm, first the classical input to be entered into quantum encoding. So CD, classical data to be converted into QD data, quantum data. So quantum machine learning algorithm to be applied here. Then we are going to measure the measurements of um, QD to CD. Then we are going to check with the prediction. So classical working here, we have discussed a classical machine learning working model with the quantum machine learning working model. So when we are going to enter the classical data into quantum model, definitely we are going to enter with a different kind of encoding mechanism. That is very, very important here. So in the working model of QM in traditional machine learning, data are directly input to the algorithm. We are going to analyze the data and we are going to check with that. In QML, receive the data as an input and we are going to apply all kind of QML encoding techniques and we are going to check with the QD data. Then we are going for prediction. So here we are just have a 3 bits of classical data and now this CD transformed to QD. Now all kind of possibilities of status of uh, each bit to be considered 2 to the power n. So 8 possible states are there. Now that QD to transform to CD. So the CD transformed to QD and the next stage we are going for QD transfer to CD. So this is the best principal mechanism of classical machine learning and quantum machine learning. So unlocking this quantum code, how this QLML working here. So encoding mechanism is very, very important. In QML, classical data must be encoded into quantum states. So this process map into different kind of encoding mechanism. The basic mechanism, the first one is amplitude encoding. Next is basic encoding and qubit encoding. In amplitude encoding, classical data into the amplitudes of quantum state. In basic encoding maps the classic data to basic state of quantum system and qubit encoding represents the data directly to the qubit state. So in the case of encoding data into quantum state, definitely we are going for parallel processing capabilities. So quantum operation and algorithms are very, very important. Quantum algorithm are central to QML. Quantum Fourier transformer, quantum phase estimation and Grover's algorithms are very, very important. This Grover's algorithm is very important to speed up the unstructured search problem. And Fourier transformer is very, very important in transforming the quantum states into frequency space. And phase estimation is very important to calculate all kind of eigenvalue associated operator. And the next is some of the popular algorithm we are having quantum support vector machine. So this is very, very important. We can easily apply this quantum with the help of QSVM. So this QSVM can efficiently handle high dimensional data and explore the multiple possible opportunity to find out the hyperplane simultaneously. And quantum neural network is very, very important here. Power of quantum gates and qubits to be represented to process the data in quantum framework. And variational quantum eigensolver VQE is a quantum algorithm designed especially for quantum chemistry problems which often involve calculating ground state energy of molecular states. VQE uses a hybrid approach. Here we are going with a different kind of optimization algorithm. Ground state energy of quantum state is very important to identify the drug discovery of material science domain. So with that idea, we are going to enter into different kind of quantum machine learning algorithm. Thank you, learners.